start the recording again here. Anyway, a question was asked about the conjugate relationship. So if it's a very strong acid, then that means its conjugate base must be very weak. A weak conjugate base means it doesn't have much of an attraction for a proton. So that means perchlorate ions don't really have a strong attraction for protons. In fact, these conjugate bases of the strong acids are so weak. You've probably seen this in the Chem lab manual. Did you look at this in the Chem lab manual? One of the handouts there. The complete form of this is in the handout. But these conjugate bases are so weak, we don't even consider them basic. For example, chloride. Is chloride a good base? Let's say, I got too much stomach acid, I'm going to take some sodium chloride to neutralize it because I see that chloride is a base. Yes? No. It's so weak that for all purposes, it's pretty neutral as far as base properties go. Does that make sense? Yeah. And so the conjugate bases of the strong acids we consider neutral for base properties. However, HSO4 minus base properties are neutral, but its acid properties are significant. But none of these others have any acid properties. None of them have any conjugate. As the acid strength weakens, then that means the conjugate base here, wants to grab and hold on to the proton. Does that answer your question, Andrew? All right, so let's take a look at those sheets. Can I pass them this way, please? Take a quick look.
Two ammonia, and 2 sodium.
Are you going to go over on the board too?
Yeah. I just want to see so can you
It's not finished. What if it's not finished?
If it's not finished, it's okay. Just turn it down. It's not working.
All right, so let's take a quick look at what we got here. Thank you. All right, so no reaction for metathesis. Another metathesis, but whether there's a reaction or not, another metathesis. I got a driving force as a solid formation and gas formation for metathesis. Another metathesis, no reaction. No reaction. I have one person reaction here, but no driving. When you do the reaction, you have to show the driving force too. Metathesis. So a lot of precipitates of manganese amide. There's a reaction. Another reaction. All right, so some people are getting it here. Yeah, so actually quite a few, except a lot of these, let's see, how many actually have it labeled the way I want it? Okay. All right, some accidentally labeled the acid and base wrong, but it looks like 4 people got it completely right. And so there is no metathesis reaction. Sodium amide, the way we treat sodium amide is the first thing is this is a soluble salt. Is there water present? Yes? Yeah, so what's going to happen? The soluble salt dissolves. So aqueous. All right, in the next, first we check for solubility. In the next step, we look for electrolyte properties. Is this a strong, weak, or non-electrolyte? This is a strong electrolyte. Soluble salts are strong electrolytes. So as far as electrolyte goes, then what should it do? It should go to Na plus and amide. You know, soluble salts are strong electrolytes, right? And so this gives us our inventory. When we do our inventories, if it's an insoluble thing, then when you inventory it, then you just leave it as solid. Now, for example, calcium carbonate. If you inventory calcium carbonate, that would just be CaCO3 solid because it just doesn't dissolve. Right, and so what we're going to do here is we're going to inventory the solution. The solution has what present? It's going to have, well, manganese is Mn2+, right? It's going to have Cl-, sodium ions, amide ions,
Water.
and water. Manganese, what are you going to put for that? Neutral. Just leave it in. And chloride is a base. Sodium ions? Amide. We don't have to write strong or weak. It's all relative. Water? Acid. So we only have one choice of acid. It's water. But we have three choices for the base. Which one? Amide. And so the people who got this, it's going to be amide plus water gives us. All right. So this is our base. This is our acid. The bases is our proton gainers, and acids are proton donors. And so we end up with ammonia and hydroxide. All right, now labeling this always tricks people into getting this wrong sometimes. Okay, what is our acid, what is our base here? Because did you know is ammonia amphoteric, or is ammonia just a base? It's amphoteric. And so it depends on what it reacts with. It could either act as an acid or a base, but normally we think of ammonia as a base. And so normally we think of ammonia as a base, and hydroxide. Is hydroxide acid, base, or amphoteric? Base. But normally we think of it as a base, but in reality it is amphoteric. And so both these species are amphoteric, which means we have to be very careful in labeling them. And so should we call ammonia the base, or should we call it the acid? Well, it depends on how it reacts. So we got to look at individually. We never consult the chart like this. If we consult the chart like this, we might get it wrong. Oops. Sorry. We have to, in other words, we have to look at the reactions on a case by case. Because a lot of people see ammonia as a pretty moderately strong base and automatically write that as a base. But that's not true. This is not a base. It is the acid. Now, how do you know it's the acid? Because going backwards, ammonia gains or loses the proton? It loses. So that means ammonia has to be an acid, not a base like we think. And that means hydroxide is the base. Now, we look at the acids or we look at the bases? We can look at the acids. Which one's a stronger acid, water or ammonia? Water. Now we go to the acids here. The acids are on the left side. Turns out water is a stronger acid than ammonia. And that means the bases must follow. So that means amide must be a stronger base than Hydroxide. In fact, amide is the strongest base on this chart, but is it the strongest base on this chart? No. Amide's not the strongest base on this chart. But anyway, what is the strongest base? Well, take a look. It goes hydroxide, sulfide, amide, oxide, hydride, and this one's called methide. It's like methane. That's the amide. Methide. Those are the ones there on the chart. All right, so actually a number of people got this one right. That's good. But lots of people didn't. You know, I want a much higher success rate than this. You know, so you want to work.
Why is Cl minus considered space?
Why is what?
Cl minus considered space.
Why is Cl minus considered a base? I don't think, because it occurs on the base side of the chart. But we should qualify this. Or neutral. Does that make sense?
Do you only know by looking at the structure? You only know that's the base by looking at the chart.
No, okay. What if an acid or base does not occur on the chart? What if an acid or base does not occur on the chart? No. It doesn't mean that it's neutral. There are going to be some species that don't occur on the chart there, but we could figure out. So let's look at something like this ion. Do you know what this one's called? It would be like propanoic acid, but it's missing the acid part. And so we call it propanoate.
I told you.
Like acetate, you know, acetic acid, acetate, propanoic acid, propanoate. This is a propanoate ion. What do you think? Is this an acid or a base, or what do you think this is? This is a base. Why? Because it can accept a proton to form propanoic acid. And so we look, can it accept a proton? If it can accept a proton, then it's a base. And so if we take this base, like propanoate, and react it with HCl, then a reaction is going to occur, because I'll tell you, propanoic acid's got to be weaker than HCl. And so we can figure a lot of stuff out, even that's not on the chart. How about this? Can this be an acid? No, there's no proton to donate. It's got to be only a base, right? So if you saw this, what would you think? It's a base, like oxide and sulfide. If you saw this, what would you think?
Both.
Yeah, both. Because it can either accept a proton to form H2Se, or it can lose a proton to form Se2 minus. And so we could figure out a lot of stuff that doesn't occur on the chart just by looking. Can it accept a proton, or can it donate a proton? And then figure it out.
Professor,
Yeah.
in that reaction, why doesn't manganese precipitate out in the presence of hydroxide?
It will. It will. The manganese will precipitate out in the presence of hydroxide, so that's good. Did you write that?
Yeah.
Okay. And so this occurs when we have multiple reactions occur. And so after we do this, we have a new inventory. Say. And in the new inventory, what do we have present? We're going to have ammonia, hydroxide, manganese, chloride, and water. Then we look, can additional acid-base reactions occur? Right? And so we can look for additional acid-base reaction, for example, hydroxide and water. Well, hydroxide and water just forms water. This would be the strongest acid present. This would be the strongest base present. We get no driving force. And so we're done with acid-base. Okay, so strongest base. Strongest acid. With these two, we get no reaction because no driving force. I'm just saving time because we don't have much time left. But what about other potential reactions? And so that's good. You saw the ion combination. This is a favorable ion combination, manganese and hydroxide. And so we end up with a subsequent reaction that occurs where we have manganese 2 plus 2 hydroxide yields which is a solid precipitate. And so this would be a secondary reaction. Second reaction occurs. But this is not what we call an acid base. This would be a metathesis. And then we're done. So good eye catching that. I'm sorry?
On the previous point, 2, right? 2 reactions.
On the previous problem, yeah, 2 reactions.
So there was metathesis.
There was metathesis and then acid base.
So is there a hierarchy of what to look for in terms of the third reaction?
Usually, the way we do this, remember I said transfer 1 proton at a time? We transfer 1 proton at a time and then see what's left over. And then see, can we get further reaction occur with the products that we just formed. And that way we can do multiple step neutralizations. You know, for example, if you're neutralizing a triprotic acid, then you got to neutralize 3 protons. And so we do that in sequence. We neutralize the first one and then see what's left over. If we have sodium hydroxide left over, then we neutralize the second one, and then we neutralize the third one, so we can neutralize all 3 protons. But we do it in a stepwise sequence. Whereas metathesis, you would do it all at once. So in acid-base reactions, and that's important to know. Let me do that. Let me say that here. Some reactions overlap. With the category. So let's look at H2SO4 and sodium hydroxide. In our metathesis approach, we neutralize it completely. In other words, metathesis, you do complete reaction. And so typically, if I'm given something like this, then I would end up with 2 sodium hydroxides, balance out, and then I'm going to form sodium sulfate and 2 waters, like that. You see? But in acid base, I just do it one at a time. So acid base, I do the inventory, and then I pick the strongest acid. The strongest acid is going to be H+, and I pick the strongest base, it's going to be OH-, and then I'm going to get H2O. This would be my reaction in acid base. But when I re-inventory the solution, then step 2. If I have excess hydroxide present, then when I re-inventory the solution, I'm going to have HSO4-, and I'm going to have hydroxide plus ... Okay. And then this is my strongest acid, this is my strongest base, and I'm going to get a second step occurs. In the second step, I'm going to neutralize the second proton with my extra hydroxide to form SO4 2- and water. And so in metathesis, we just go ahead and do the complete reaction. In acid-base, we always do it one step at a time, see what's left over, and then do a subsequent step after that. But this applies for all reactions as well. In all reactions, we don't usually stop. Let me give you another example of a reaction where we don't stop necessarily, and then it doesn't always have to go in the sequence that I mentioned. This particular reaction does go in the sequence that I mentioned, but it doesn't always. So let's try this one. Iron 3. Let's see. Iron 3. Iron 3 chloride and silver nitrate solution. This is what I'm going to do. So we have a sequence of labs that deal with the chemical reactions, and we're going to be working on those. And so I'm going to kind of spread out the chemical reactions section. Since I'm going to spread it out, then what I'm going to do is I'm going to start talking about Chapter 6 in the meantime. And so we'll start with some Chapter 6, probably tomorrow, this week. A little bit of Chapter 6 while we're discussing Chapter 5. And we'll just keep going through Chapter 5 until we finish it. But try this one. So what do you do? You start off with metathesis, and then you work to acid-base, and then redox.
So if we know there's a metathesis, like, then we have to check for acid base as well.
Well, that's a good question. If there is a metathesis, can you stop there? And so, let's see. Actually, since we're running out of time, let me just go ahead and write this. FeCl3 plus AgNO3, right? Well, this is just a regular double replacement metathesis reaction. It's going to form FeNO3 plus AgCl. Chlorides, bromides, iodides are insoluble, except except for silver, lead, mercury. Yes. And so we got a driving force, which is precipitation. So we need how many of these? 3 silver nitrates and 3 silver chlorides, and then it's balanced. Okay, this would be the complete, and then what would we do? We'd write the ionic equation and the NIE, and then we'd stop here, right? This is normally where we stop. We don't look for other reactions. But it turns out there is another reaction that occurs in this one. And so, what is the other reaction? Well, it turns out, is it acid-base? What do you think? Looking at these species, looking at the inventory, do you think acid-base? No. No, I mean, nitrate is so weak. so weak, we call it neutral. Chloride is so weak, we call it neutral. Silver ions are those good proton acceptors and proton donors. They're neutral. Well, iron 3 is tricky. We'll talk about iron 3. Iron 3 is what we call Lewis acid. Iron 3 is up there on that chart over here. Is it on this chart? Yeah. Iron 3, and we're going to talk about this when we get into Lewis acid bases more. And, iron 3 is actually a Bronsted acid. It forms this weird thing here. I'll talk about that later. This is Chem 1B type stuff. But still, nonetheless, no reaction. And so it turns out there's no acid-base reaction. And so yes, metathesis reaction there is. Check. Acid-base? No. No reaction. Good. But we still have one more type of reaction we have to consider. What is that? Redox. Now, the thing is, there could be a redox reaction because we never considered it, right? And it turns out, yes, there is. There is a redox reaction. And so how do you figure out the redox reaction? Well, let me write down the steps and then we'll look at. Step 1, inventory. So it's just like acid-base. We inventory it. Step 2. We find the strongest oxidizing agent. OA. Now the strongest oxidizing agent, the strongest on our chart here is at the top left. What's at the top left over here? Fluorine. And so, we look at the chart over here, and then, oops, see if I can lift this up, and then see where it is in relation to fluorine. F2 side, right? 3, find the strongest reducing agent, or RA. What's the strongest on the chart? So, these are apples or oranges. What's on the other side? I mean, let's call those the oranges, then we've got to look on the apple side and figure out which is the biggest apple, which would be lithium. So this is the lithium side. So you got to remember those. And then we react the strongest OA and RA. By combining this one, we're going to use the half reaction method. We have to. By combining half reactions, making sure that the electrons
Cancel out.
yes, cancel. Thanks.
Why does it say there?
React the above by combining half reactions, making sure that the electrons cancel. Okay, then we clean it up, simplify, eliminate spectators, and determine driving force. Driving force for redox is simple. We want to go from stronger oxidizer and stronger reducer. Because of the conjugate relationship, this has to fall to weaker oxidizer and weaker reducer. There's a conjugate relationship between this. And so let's talk about the conjugate relationship briefly, since we're running out of time here. But the conjugate relationship is just like for acids here. So, okay, this is tilted, so sorry about that.
These are two different charts, right?
Yeah, these are two different charts. This on the left is called the redox chart. This on the right is the acid chart. This is the exam version I put on Piazza. The exam version is what I'm going to hand out with the test. And so you should get familiar with these two charts. All right, if fluorine's a powerful oxidizer. Powerful oxidizers are electron poor or electron rich. Electron poor. Powerful oxidizers are electron poor. And so fluorine's a powerful oxidizer, it really wants electrons. Once it has those electrons, is it going to let go of them easily? No. And so this is the conjugate relationship. A powerful oxidizer means its conjugate reducer is very weak. And so a good reducer is electron rich, it wants to give up the electrons, right? And so that means fluoride is an extremely weak reducer when fluorine is an extremely powerful oxidizer. That's the conjugate relationship. We can see it at the opposite end of the extreme for lithium. Lithium is a powerful reducer. Powerful reducers are electron rich. That means when it loses the electron, which it loses easily, is it going to want to get it back? No, that means lithium ion is an extremely weak oxidizer. That's the conjugate relationship between oxidizer and reducer, just like we have the same thing. You know, if methane is an extremely weak acid, it doesn't want to give up its proton. So if it gives up its proton, you better believe it's going to be looking for another proton to replace it. And so that means methane, a very, very weak acid, makes an extremely powerful base. Okay, we're out of time, so I'm going to stop here.